Hopefully you remember last time we introduced this new idea, which is to virtualize the computer memory. Okay. So we wanted to not have programs talk directly to physical memory anymore. That's sort of the fundamental idea behind memory virtualization. We want to have some way of having an intermediate step between the addresses that programs use and the addresses that actually make it out the memory bus to the memory modules. So we started about dividing the memory itself into pages. So this is going to be some power of 2. On x86-64, I told you last time the punchline is 4 kilobytes. And it's been that way actually for a really long time. The 4 kilobytes is the page size on these systems. It's not required. There's been other systems with 1 kilobyte, other systems with 8 kilobytes. It just sort of depends on various details of system design. But we pick a power of 2. And then we're going to map each one of these virtual pages to a physical page. Now, you'll notice that we're introducing new terminology here, and I want to make sure to point this out. We call these physical pages frames because the contents of the physical memory actually is less relevant. It's as long as it's the memory data that the program is expecting to be at that location. So it's kind of the way that we call it is that you have the virtual page and the physical page frame. And it's just like if you had a wall of picture frames and you could change what picture was in it. Okay? And so that's why the physical page frames are called frames, because we really care more about the data in it that's, whatever a program expects it to be, as opposed to where it's physically located. We don't really care where it's physically located anymore. Okay, and then that mapping is specified using a page table where each entry says this is where the corresponding, I'm sorry, let me see if I can say this correctly, where the page is stored in a physical frame. Sorry, I bit my tongue last night and I can't talk as well today. I don't know, it's like really irritating. It's right on the tip. Okay, anyway, so we have hardware support for this translation because it would be really dumb to do this in software. In fact, well, you're not even seeing that in software for Lab 8 because we're not doing any address translation. We can't really do it at all in software. But if you were to implement it in software, it would be horrible. And so there's a special component called the Memory Management Unit, which takes care of all of this address translation. So that's silicon, and it knows how to interact with the page table to do the address translation, virtual to physical address translation for us on the fly. Okay? Let's see. So we had the virtual, remember we had the virtual address, and since the page is always a power of 2 in size, we know that some of those bits in the virtual address will correspond to where in the page we're accessing. So that's the virtual page offset. Since the physical frame and the virtual page have to be the same size, I think that makes sense as well. The virtual page offset comes straight down. We don't do any translation on that at all. And then the virtual page number is used to index into this page table to look up the corresponding physical page number, or if you will, the page frame. Because again, that physical page number and page frame are equivalent terms. Okay? Let's see. And then we have a special register which says where this table is located. Okay? And so that way we can have multiple page tables. Each process can get its own page table. And a context switch, let's say part of the context switch process is now changing the page table base register from pointing to one page table to pointing to another page table. And then that just changes completely what memory looks like for the process. Okay, any questions about this mechanism? This is the cool new mechanism that we introduced last time. Okay, and this suddenly gives us a lot of power as far as being able to construct programs, processes that have completely isolated address spaces. Now, so we talked about that. The one thing that we left off on is that we still have this issue that we are limited to the amount of physical memory that we have. And if you have a program that's stopped, well, it's still taking up memory pages, and so we'd like to get those back somehow and figure out how we could use those frames to support other programs that maybe actually need them a lot more. So this is the thing that we're going to try to talk about today. Okay, yeah, so we already know that processes aren't always active. So what we're going to do is change this idea a little bit so that now our virtual memory system will actually be a cache of data on disk. So now the actual memory that we have that programs use is disk memory. It just happens that some of it is brought into DRAM, and so we get the performance of DRAM and the size of the disk, which is pretty cool. Okay. Now it's funny because we already talked about how slow DRAM was compared to the hardware caches, and so you can see how this mechanism trickles all the way down. Now what we're saying is we're going to have programs, if they're written with good data locality, so they have good locality of access, then we should be able to get a memory the size of our disk at the speed of SRAM. And in general, we actually come pretty dang close. It's only when we have situations where we need to load data or we have programs that are particularly badly behaved that we start seeing the lower memory performances. Okay, so remember we had our cache lines. We had to have some way of keeping track of what block of data was in the cache line. We had to know if there was even any data in the cache line. We had to know if it had been written to. We had some bookkeeping details like that. So we're going to start applying the same ideas to our virtual memory system. Is a virtual page cached in DRAM main memory? Or is it on disk somewhere? Is it even been allocated? Is this address range even available for the program to use? You all may remember that, when you dereference null, your program crashes. Well, something in your computer is saying address 0 is not a valid address. Yet, if you have your memory pool, or if you're talking about on assignment 8, you have your memory mapped regions. When you access those addresses, you can have different behaviors. So clearly this is something the operating system has to keep track of. So yes, this is cool because now we can overcommit memory. So we can basically hand out a lot more memory than we actually physically have, because the reality is that programs aren't always using all of their address space. In fact, they typically are using a relatively small amount of their address space. Okay, so DRAM access latency, remember it's like 50 to 200 clocks, something like that, so 50 to 100 nanoseconds. Disk latency is going to be up to 30 milliseconds, which is terrible. Okay, so now we have cache misses that are going to be very expensive. But the thing that we notice when we look at this is that the disk has a pretty good throughput. Now I have here 50 plus megabytes per second. Has anybody measured the disk throughput on your computer? Like a couple of you have. Do you remember what it was?
That was an SSD.
So what was it? A couple hundred megabytes per second? Is that what you found as well?
Because I have a PCI one, it's closer to more like a gigabyte or two.
Okay, yeah, so you guys are lucky. When I say 50 megabytes per second, we're talking even all the way down to like slow spinning disks in laptops. Typically laptops will have a 5400 RPM drive to save power. Typically desktop computers, if they are still saddled with a spinning magnetic disk, will be 7200 RPM or up. And so you tend to see multiple tens of megabytes of throughput on those devices. Solid-state drives get a lot better. RAID, even better, because now you're talking to a bunch of disks in parallel. And if you want to get super fast, then you start doing RAID arrays of solid-state drives, and then you have blazing speeds. So that's a real lower bound that we're saying here. But the point is, the upshot is that if I read the first byte, and that costs me 30 milliseconds, then I'd be dumb not to just get a whole bunch, because the throughput is pretty high on these devices. And so if I get 1 byte, then that's going to be 8 to 30 milliseconds. But if I get 100 kilobytes, well, you can do the math, and you can do really conservative throughputs and use that to come up with an estimate, and you discover that you're not adding much time. Now, we don't transfer 100 kilobytes. Remember, I said that the page size in this virtual memory system is 4 kilobytes. So it's going to be 8 to 30 milliseconds plus a little bit of change. Okay? Not bad. Okay? So we'll stick with that. So we choose a large page size. Okay, and that will allow us to make up, sort of make up a little bit for the cost of accessing this device. And that will hopefully help us to reduce the number of misses because we'll bring more data in each time. Okay. Also, since this is controlled by software and since we have so much time to wait thinking about which page we should have chose and so forth, then we'll actually go ahead and use very sophisticated replacement policies and very sophisticated placement policies. Both of those will be sophisticated. So a lot of times the operating system will actually use a hash table of some kind to say this block is located here in memory, and that means it can be placed anywhere. We don't really care about really simplistic placement policies at this level. Okay, and also we will use write back because it would be dumb, again, to do write through. Every time you have a memory write, you go ahead and write it back to the disk. That would be really sad. So basically we accumulate a bunch of writes in memory, and then eventually we evict that page and write it back to disk. Now you'll notice that that means that our OS needs to be shut down cleanly, because if it's not, we'll lose whatever writes occurred in memory. Okay, so that's just one of the realities of how these systems work. Any questions about any of this? This is pretty important and basic stuff for how this all works, how this all hangs together. Okay. Now we have page table entries. Remember, we had cache lines. These are the virtual memory equivalent of a cache line, so it's a page table entry. Basically, we need to have the additional bookkeeping that we talked about before. So we have a valid bit, which basically says, is this entry even meaningful? Okay, so valid 1 means that the page is cached in main memory. Okay, so that's cool. That means that that page table entry can be used for address translation. Valid of 0 means that if the MMU is doing the address translation and it pulls that page table entry and it sees the valid bit being 0, it's like, oh, that's not in memory. I can't use this for address translation. So the question is, what does the MMU do? Well, unfortunately, at this point, the MMU can do nothing. Okay, if it's not in memory, it can't do address translation, so the MMU has to get the operating system involved. Okay, let me see what else I say here. Oh yeah, so this is kind of an interesting thing. You have the entire page table entry. Now on x86-64, it's 8 bytes. 1 bit controls whether or not the MMU uses that entry. So when the valid bit is 0, the OS can actually use the remaining bits of the entry to store other useful information. So for example, Linux will use the remaining bits to say, this is the swap device, and this is the location on the swap device where this data is actually stored. So you have a lot of different ways you could actually use the remaining bits in that page table entry to say, yeah, this is valid, I just don't have it in memory, I have it somewhere on a swap device. Okay, any questions? Make sense? All right. Let's see, so virtual memory, yeah, so the processor is able to do part of this. In fact, this is probably the most important point of interface between the computer hardware, which is sitting obviously on the chip and on the motherboard, and then the operating system above it. So, like I say here, the address translation is done in hardware. The MMU uses the page table to do the address translation. Who sets up the page table? Well, the OS does. Every time a process is initialized, or it calls mmap or munmap or malloc or anything like that, the page table may change. The processor can't take care of all of this on its own. So when we have a situation where an address is emitted by the program, and the MMU looks at it and can't translate it for some reason, typically because the valid bit is 0. Okay? So then the MMU has no idea what to do. So this is where the OS, again, must step into the picture. Okay, so the virtual memory system is where the operating system and the compute hardware have to work very carefully together to provide this virtual memory facility. Okay? So we have a simple example. I'll show you. I'll just give you the punchline. Anytime you do something where the MMU can't figure out what to do about it, you get a fault. Okay, remember that a fault means you have an instruction, its execution couldn't be completed, And so the MMU will trigger this fault, and the OS will step in and decide what to do about it. Okay? If the OS can recover from it, like let's say that it's a page that just needed to be loaded into memory, then the OS will return from its fault handler, and that'll go back to the faulting instruction. So the faulting instruction will get to go again, and perhaps this time succeed. If the fault happened to be something like your program dereferenced null, well, then the OS will say, that was dumb, the program needs to terminate. And so it'll take care of that side of things. The MMU won't go ahead and try to run that instruction again, because that would be silly. Okay? So anyway, we have this simple example here. We have a virtual memory. Notice our page table is nice and simple. Only 8 entries, because we have 8 virtual pages. We only have 4 physical page frames. So you can see those in the top right. I've labeled them on the right with what physical page number they are, and then also what virtual page occupies that physical page frame. And then you can see the disk has a number of pages as well. Okay. Some of these are in DRAM, so you can see just looking from the page table which ones have valid bits. So PTE1, PTE2, 4, and 7. So those are cached in DRAM. Okay. Some are only on disk. So you can, again, spot them really easily because they have dotted lines. So PTE3 has a valid bit of 0, but it also says this is where the page is actually stored. And PTE6, same thing, says this is not valid, but the address says where it is on disk. And then you have 2 pages that are not allocated. So you have 0 and 5, which have details saying this is not allocated and it's not on disk. All right, does that make sense? You can already see that there's some details here. There's some bookkeeping details that the OS has to keep track of to make this mechanism work. The OS has to be able to distinguish between entries that have a valid bit of 0 and are unmapped, and entries with a valid bit of 0 that are mapped, but just not in physical memory. It has to distinguish between those two. The MMU is like, I don't care, valid bit is 0, your problem. But the MMU, if the valid bit is 1, it's like, I can deal with that. I could totally handle that situation. So, we have the first access. We don't care what address specifically, it just happens to hit virtual page 2. And so think about what the MMU does. You know, the program emits an instruction that goes through the MMU. The MMU says, oh, virtual page 2. And so it goes, looks up in the page table, PTE2, valid bit's 1. Awesome. Right? So it turns around and says, page table entry 2 says that virtual page 2 is stored in physical page 1. So it does that mapping. That's the address that sent out the memory bus. And then the memory sees the access on physical page frame 1. Okay? Just one second. Let me see what else I see here. Yeah. So cool thing is, OS has not been involved at all. This was taken care of entirely by hardware. Okay, so the program doesn't know that it's accessing physical page 1. It sees itself as accessing virtual page 2. The compute hardware took care of it all. Okay, question?
Since you have unaligned accesses, what happens if you split across a page boundary for one page zone?
Yeah, so this is a good question. What happens if you have an access that crosses page boundaries? Well, already it's going to cross the data bus word size boundary. And so it's going to be 2 different memory accesses that are reassembled. The data pulled is going to be reassembled within the processor. So if you had, for example, a read at the end of virtual page 2 that spilled over into virtual page 3, the part of the access that was in virtual page 2 would just happen. No problem, right? Because the MMU is like, I can deal with that. But then you would see a second access that was at the start of virtual page 3, and the MMU would say, I can't deal with this because the valid bit's 0, and it would raise a fault. So the OS has to get involved. Does that make sense?
What happens if you would have to evict page 2 to page 3?
That's a really good question. So what happens if you evict page 2 to load page 3? Well, those are the kinds of situations where the kernel needs to make good choices. And if it doesn't make good choices, then probably no one will want to use your OS because it'll be really slow. Okay? So the kernel has responsibility to make good choices about what pages are paged out. Yeah. Hopefully some of you are seeing that by now on assignment 8. it's possible to make that program run really slowly by making bad paging choices. Which is why I hope nobody's using the NFU policy. Not frequently used. That's where you just have a counter for each page. How many times has it been accessed? And you use that. It doesn't know anything about recent history versus distant history. And when I wrote NFU and ran it on the software for assignment 8, it was horrendously slow because you have like millions of page faults that occur. Makes you sad. Okay, any other questions? All right. Let's see. So let's say that we access a word in virtual page 6. So this time, of course, the MMU looks in the page table, virtual page 6. I can deal with this. And it goes down to the page table entry, and it sees a valid bit of 0. So it's sad. It says, I can't deal with this. Okay? So the MMU raises a fault. Typically, we call this a page fault because we're talking about an access where the corresponding valid bit is 0. We do have a different kind of fault, which we'll talk about in a moment, but page fault would be, I can't do the address translation at all. So the kernel gets to step in and deal with this. Okay? So the kernel looks at this and says, oh, virtual page 6, guess what? That's actually on disk. So all I really need to do is load virtual page 6 off of the swap device and load it into physical memory, update the page table entry to say now it's in memory, and then I can return from my fault handler. The processor will try the instruction again. This time it'll succeed. Okay, that's the idea. Okay. So, first issue though is we have to pick somebody to evict. Okay, so you can see that this is going to take a little bit of time. The kernel has got to select somebody. So let's say it thought very carefully and decided to evict virtual page 4. Because again, when it looks at this, it's not really looking at the physical page frames because it's indifferent as to which frame this is in. It doesn't care which frame it loads virtual page 6 into. So it's looking at the existing virtual pages, the virtual pages that are in memory. And it says which one of these has been accessed, for example, furthest in the past. Which one of these is most likely to not be accessed in the future. It'll evict that one. So let's just say for whatever reason it chose virtual page 4, writes it back to disk if it was modified. And then it'll update the page table entry for that virtual page saying this page is no longer in DRAM. Okay, so notice the valid bit gets set to 0. The data inside the page table entry says now it's on disk at wherever. Okay. So now there's an available frame, and the kernel can load virtual page 6 into that frame. And then it can update the page table entry so that the valid bit is 1, and the entry actually says this is the page frame that it's in. Okay? So then it will return from the fault handler. Instruction is tried again. So the MMU gets alerted again. Hey, MMU, we need to do an address translation. So it goes and looks at virtual page 6. Hey, the valid bit is 1. So it does the address translation, and off we go. Okay, any questions? This is a page fault. This is page fault resolution. Yeah, question?
Can you context switch to another process while it's doing this?
Yeah, can you context switch to another process while this is happening? Why might we want to? Yeah, remember that page faults, if you can actually resolve it by loading data off the disk, now you're talking to a disk. Sad, right? So that's going to be milliseconds of time that you're wasting. So page faults are a specific case in which context switches frequently happen. They have to happen because we want to go do something useful while we're waiting to bring that page into memory. Okay? So what does that suggest about page fault rates? Is it okay to have a really high page fault rate? Probably not, right? Because we're losing a lot of time context switching. Remember what I said? Context switches are not useful work. So we'd like to keep the page faults to some reasonable minimum. Now, if we lived in a perfect world where everybody had like the entire address space available on the processor as physical memory, so everybody had like 256 terabytes in their computer. That would be awesome. Well, in that case, we'd never have any page faults. But the reality is you're always going to have a few because, like my laptop, I can't even remember. I think I have 16 gigs of RAM. So I run out. But the thing about it is that programs don't always use all of their memory. And so sometimes you want to page out some of that. Page faults are a good time to reclaim that memory and use it for another program that needs it. So you always see a certain basic level of page faults occurring, but if it gets too many, then you're going to be sad because you're losing time doing other things. And if you get to the point where the I/O system is saturated and you're spending all your time handling page faults, like this is the whole issue of like if you were accessing page 3 and it paged out page 2, but you just wanted to go access page 2 again, well, now you actually are waiting more on I/O than you are utilizing the CPU. And if the CPU is sitting idle and the I/O system is completely slammed with page faults, now you're thrashing. And your entire program or your entire computer system is going to slow to a crawl. Okay? So there's this real balancing act. Okay, program needs more memory, so we can allocate more memory. So this is the whole issue of virtual page 5 was unallocated. That address range was not available to the program. If a fault had occurred there, the operating system would have had to say, you don't have anything in that address range, you're terminated. But if they called malloc or they called mmap or something, and now they wanted to actually have page 5 available, then what the OS can do is update that page table entry to say, yes, the valid bit is still 0, but when somebody accesses it, then go ahead and pull data from here. Okay, and so you can notice that we've updated our virtual memory on disk that, okay, now there's a virtual page 5 loaded from somewhere, but it's still not in memory. The whole reason why we like this idea, this approach, is that we don't want to assign a physical page frame to a program until we know it wants to use it. How do we know it wants to use it? Well, if it faults on that frame, or I'm sorry, if it faults on that virtual address. Then we know we need a frame, so we go ahead and page something out, and we have a frame available. We map that virtual address to the frame, and then we let it go. Okay? So that way we can give programs pages on demand. That's why this is called demand paging. Okay? If the program demands it, then we'll let it have it. Okay, any questions? Let's see. So now DRAM is a cache. Hooray. But this is the one thing that I want to mention because this is a little bit new. It's funny because virtual memory actually existed long before any of us existed. Maybe not long. I mean, I was born in 75. But virtual memory was designed in the 60s. So you may have been here when I showed you those little magnetic toroidal core memory modules from various old computers. Those computers supported paging. Now they used magnetic cores and tape, not SSDs and DRAM modules, but same thing. They were able to do this paging trick. Okay, so caches store blocks. Remember, a block is the chunk of data that's brought into a hardware cache. Virtual memory, we talk about pages and page frames. Okay, so just different terminology. Okay, caches have cache sets and cache lines. Now, virtual memory doesn't have cache sets because we don't have a placement policy. We just have a very general purpose placement policy. It could be anywhere. Cache lines are the things that keep track of a block, so they hold the block data and they keep the bookkeeping information as well. And virtual memory has page tables and page table entries. The page table entries correspond somewhat to cache lines, but page table entries don't hold the page data. Cache lines hold the block data. Page table entries just say where the data is located in physical memory. Okay? Caches have cache hits and cache misses. Virtual memory has page hits and page faults. Okay? Very similar concepts here. All right? So just make sure that you are aware of the difference in terms. And so different These different subsystems have different terminology used, and they don't always mean exactly the same thing. So this is your chance. Do you have any questions about these terms? Okay, hopefully it all makes sense. Now, virtual memory does depend on locality. In fact, you notice this a lot, that if you have a program that behaves well from a hardware caching perspective, then it will probably also do well with virtual memory, because it's already going to have good locality of access. The cache blocks are 64 bytes, so it's working with the cache very carefully. Well, then it's probably going to work really well with the 4 kilobyte page size as well. So virtual memory will be pretty happy. Okay? Where sometimes programs run amok is this number of virtual pages they need to access. Okay? Because if they get to a point where the number of virtual pages they're working with is larger than the number of frames that the computer has, then you're going to have a problem. You're going to be generating a lot of faults. And so, like I say here, a program as it's running will be working with a certain memory region. So that will take up a certain number of pages. And so we call that the working set. Those are the pages that we really want to have in memory. So, like I say here, if the program has good locality, the working set will typically fit within memory and will have good performance. And if it doesn't, then we'll be sad. What else do I want to say about this? One thing that's kind of challenging is the program doesn't say, hey, computer, this is my working set. Windows actually has a way of saying, this is what I'd like my working set size to be. But most of the time, the program isn't so helpful and says, these are the pages that I'm working with. You have to observe this. So this is another one of those things like process scheduling, where the OS has to watch what's going on to figure out what is the working set size of a program. Okay. So if you have a working set that's too large for the number of frames, then like I said, you're going to touch one page, and maybe it generates a fault, and the OS is like, oh man, now I got to load that page off of disk into a frame, and so it does that, but it evicts another page that's also in the process's working set. So you get another fault the next time you have an access. So you generate a lot of faults in this kind of situation, and so we call that thrashing. Okay. Now, maybe this is very uncommon for you, since we all have tons of memory and programs are reasonably well behaved. But this was really common when I was a kid. When you'd have your computer, and it'd be like this big box. It was a big slow box, of course, because computers were a lot slower back then. And you might have, a megabyte. You might have 4 megabytes. I mean, I'm talking like really luxurious computing power there. 4 megabytes of RAM. And you've got your, maybe you're lucky and you have like a 1 gig disk or something like that. And this virtual memory abstraction was implemented back then. But you would see, you'd run some programs and all of a sudden you'd see the disk light was just on all the time and your whole computer was running really slowly. Well, it was thrashing. Is spending all of its time servicing page faults because some bad program was trying to use a working set larger than the physical memory size. Okay? Tends to be very uncommon these days. It tends to be really difficult to get that to occur anymore because we just have so much memory to use. Most programs don't actually get anywhere near that memory size. Okay, any questions on that? All right, so maybe you're lucky and you've never seen that. There is a cool function on Unix called getRUsage. getRUsage basically tells you things about what the process is doing with the hardware resources. And so, for example, it will tell you how many page faults your program has generated. And so this is really helpful if you're writing a server or something like that, because then you can diagnose, am I generating too many faults? Is my working set too large? Do I need to tune my working set size to match physical memory resources better? Things like that. Okay, so it can be really useful for this kind of thing. Okay? Yes?
Is this function like a real-time updating function? Is it just like when the program ends, it gives you a report at the end?
I believe this is sort of updated as you go. And so you can call it, you call it within a process, and it'll report that process's details. So it's a system call, as you can imagine, because the kernel is involved in maintaining this information. But yeah, you could call it periodically, for example, and see what's going on in your program. I think there's also ways of getting the global details as well. There's a program called VMstat, which you can use as well. You can just run it. You can run it on a periodic interval to watch and see, do I have a lot of faults? Am I generating a lot of faults? And so forth. So VMstat is another tool that will report that stuff on a global basis. Okay, any other questions?
I guess on the same function, does it report everything as like just output to the terminal, or can you get numbers that you can use?
No, this is the kind of function where I believe you either pass in a struct or you pass in some argument that says what statistic you want, and an out parameter, and it'll give you that detail. Yeah, most of these system calls do not output stuff to the console because they realize that programs may want to actually utilize the results. Okay. Any other questions? Alrighty. So we have disk-backed virtual memory now. Let's see what time it is. Okay, we still have some time. We use this system extensively for running programs. Because if you think about it, I've got a program, it's a binary. We've been talking about this sort of informally all the way along, and you probably know this, but maybe you don't know what is in that binary. Well, it turns out that there's sections in that binary, and the header data in that binary file says, this is the address where this part of the file should be loaded. And so when you type whatever, you're running a program from the command line, what happens is the OS steps in and it says, oh, I need to map this part of the binary to this region of the virtual address space. So we can leverage a virtual memory system for this. Okay? So we start a new program. Kernel will simply allocate a set of contiguous virtual pages. So it's going to update the page table saying, here are some page table entries. But it doesn't have to map those into physical frames yet. It can use a demand-driven approach. And so it can go ahead and map those entries, those virtual page table entries, to the parts of the file that correspond to the data that should be loaded. Okay? So now think about it. You've got this page table for the process. It's got all these entries at the right address ranges, but they're still pointing to the binary file's contents. And then you start the program. So first line is executed, the first instruction. You get a page fault. Well, now the system knows I need to load that page, and so it loads it in and begins running the contents of that page. So 4 kilobytes is a lot of machine code, so that runs for a little while, and then it tries to go into the second page. Another fault. So then it loads the second part of the binary into a physical frame and resumes executing. Okay? So you can see that this mechanism is really powerful to make sure that we don't give a program more physical page frames than it actually needs. Okay, again, that's called demand paging. Are there any questions about that? One thing you might say to yourself is, seems kind of silly to require the system to page fault on the very first page of the program. That might be a good observation. And so a lot of computer systems actually do what's called prefetching. They'll load the first page, or they'll load the first n pages of the binary because it knows they're going to be accessed right away. So that way, if you have enough frames available, why not do that, and then it'll be faster to get your program running. Okay? Instead of that compulsory 8 to 30 millisecond delay, the program is loaded already, and it just starts ripping away. Any questions? All right, so you can see there's a lot of different ways to design these systems. Okay, yeah, so memory mapping is the technique that I just described, where you have virtual address ranges that are mapped to a file, but the entries are not valid, or maybe they are, and that just means that that part of the file is mapped into memory, and you can access it in DRAM easily. So there's a special function called mmap that allows you to manually control this stuff from the user process. Again, if you started assignment 8, you're already familiar with mmap. Okay? Notice you give it a start pointer, and also a length. So that needs to be typically at the start of a virtual page boundary and be some multiple of virtual pages. And you can go ahead and say, I want to map this virtual address range to this file. So that's the FD part, so that's file descriptor. You can give it any file pretty much. And then you can say what offset from the start of the file. So basically what this allows you to do is to interact with a file's contents as if it were just already in memory automatically, and you do it through memory accesses as opposed to actually having to call read and write to interact with the file. Okay, that's called memory mapped file I/O. Are there any questions about that? Yes?
File descriptor is pretty general.
Yes.
File descriptor.
What is that file descriptor? I couldn't tell you off the top of my head what the requirements are on that file descriptor. I don't think it's allowed to be any kind of device that's not... yeah, it probably has to be seekable. It probably has to be a seekable block device to work properly. The reason why I say this for everyone else in the class, if you don't have a lot of systems programming experience yet, is that standard input and standard output and standard error also have file descriptors, 0, 1, and 2. Okay? A socket, if you open a socket, has a file descriptor. Can't really use sockets with this mmap call. And you can have other things like pipes and a few other things. You can have a lot of other things that have file descriptors as well. So in this case, the file descriptor kind of really needs to correspond to a disk-backed file. Or it could be backed by a RAM disk or something like that. But it needs to be some kind of block device that supports seeking. Okay, any other questions about this? mmap is really, really cool. It's used by a lot of programs that want to have really fast disk I/O. And you can imagine that this is actually leveraging the OS's virtual memory facility to do this really fast. So now you want to load part of a file, it's handled through the page fault handler. There's not a separate explicit call to load that data. It's loaded automatically. And again, when it's saved back to the file, well, that's, page eviction. Okay, so, like I say here, we can use a virtual memory system to load programs and read-only data. And if you look at this and say, loading programs, I probably don't want to allow programs to modify their own code. Even though you can write some really clever, cool, crazy programs that are self-modifying. It's a really bad idea in practice, so we try not to allow it. And same thing with read-only data. If it's read-only, we should probably enforce that. So you can imagine that page table entries also have permission bits saying what operations are allowed. Okay? So notice our page table entries now, we still have the valid entry. Is it 0 or 1? Is it invalid or valid? We have the physical page number, but then we have a few other details that say what we're allowed to do to that address range. So read-write, if it's 1, we're allowed to write to it. If it's 0, we're only allowed to read it. And then you have supervisor. So that's your kernel mode. Are you only allowed to access this address range from kernel mode? Or can you access it from user mode or normal mode? Okay, so this allows you to start putting protections into your virtual address space so that you can control what things happen. Okay, so you end up with something like this. This is sort of a typical memory layout. Okay, you have, and it's actually changed because of Spectre and Meltdown and these other timing exploits, which make us sad. But it used to be, up until a few months ago, that we'd have a whole bunch of the kernel mapped into every process's virtual address space. But it was marked supervisor mode only, so that could only be accessed by the kernel. Okay? Turns out that processors were designed in a way that was intended to make them fast, but allowed user space code to actually identify the data in kernel mode, which made everybody sad. Okay? So anyway, we have shared libraries as well. They're read-only, as they should be, because everybody's sharing them. They're file-backed. You have the process stack, process heap. Those are read-write, and local only to the process. And then you have program code and program data. The read-only data and the program code can again be shared across multiple processes. If you think about how many terminal windows you have open, or how many web browser windows you have open, why load that code into physical memory more than once? Load it once and just map it into each process's address space that's using it. Okay? Does it make sense? This is the cool, powerful things we can do. So if the code tries to do something, remember that I said if MMU translation occurs and the valid bit is 0, we get a page fault. Well, what if the valid bit is 1, but then the permissions don't match the operation being performed? You have an instruction fetch on something that's not executable. Or you have a write occurring against a read-only chunk of memory. Well, then we get a protection fault. And so again, the OS can decide what to do about it. Now I say here that the typical response is to terminate the program, but it turns out that there's some really clever things that you can implement by not necessarily just terminating the process. So we have other reasons why we might want to do something other than simply terminate the program. But this is what the OS and the hardware are doing. Okay? Make sense? All right. Last things that I want to talk about today. I think we can get through them in the last 6 or 7 minutes. There's some actually really huge, serious implementation issues that we need to resolve. First one is, where do page tables live? You can see in our picture is misleading because we have main memory, which is only 12 cells anyway, but we have this big main memory, and we have the page table sort of hanging off the side. That's not accurate, right? A more accurate picture is that the page table is living in main memory as well, right? So what happens when we're doing address translation and the MMU needs to look up an address from the page table so it can map it? How slow is that going to be? It's going to be pretty gross, right? We're doing address translation. We don't want to pay the memory access price just to do our address translation. So you can see that this design, the way that we have it specified so far, has this massive performance issue. What do you think the solution is? Well, same solution we talked about in week 5, right? Caching. Caching is key in these kinds of systems. So main memory is slow, so we don't want to incur that cost all the time. Now, maybe we're really lucky and our L1 cache happens to hold part of our page table. Okay, that's nice, but now we're losing part of our L1 cache to page table. I'd rather not do that. I'd rather have my L1 used for program data. Okay? So, the way that CPUs are designed is they will have a special cache that is right next to the MMU, and the MMU gets to squirrel away details about address translation so that it can look it up later. That's called the translation lookaside buffer. Okay? And so this TLB memory is super fast, because if you think about it, remember, the larger the memory, the slower it is to access it, the slower it is to address it. So if we can make that memory small, well, remember that page table entries are 8 bytes. 8 bytes is a tiny block. So the translation lookaside buffer has cache lines that are really tiny. They're really fast to access. And it tends to be that the TLB cache is small so that it can do this lookup really fast. It can decide if there's a hit or a miss really quickly. Okay? So that's super fast. Typically, this will be pretty associative. So you'll talk about like 4-way set associative, 8-way set associative, so that various memory access patterns won't destroy performance of address translation. Okay? But you can see here, like I say, the input is a virtual page number. The output will be the page table entry so that we can look at the permissions and we can do the physical page frame. We can use that to emit the address. Any questions? This is really important to make sure your computer doesn't suck. Okay? The fastest cache on your entire processor. Okay, so that's the first one. I'm going to point it out again. TLBs. Everybody's friend is the TLB. Okay, second issue. How large is the page table? Remember I guessed how large it was last time. Okay. 48-bit address space. We'll just do this math for x86-64. We have a 48-bit address space. It will eventually be expanded to 64 bits, but it isn't right now. And we said that each page is 4 kilobytes in size, which means we have 12 bits used to access within the page, which leaves us a whopping 36 bits left over that we map. That's the virtual page number, and we have to map that to a 36-bit physical page number. Okay, so how many page table entries? Well, what's 2 to the 36? Big, right? 2 to the 36 is big, and then you take that and you multiply it by 8 because each entry is 8 bytes, right? So what's 2 to the 39? It's also big, right? This is the size of a page table in bytes for this kind of a system, okay? So you have 64 gazillion, I think that's what the G stands for. No, it's 64-ish billion entries, okay? And since each entry is 8 bytes, the entire page table is going to be 512 gigs. And we get one of those per process. That's horrible, right? We don't want to waste 512 gigs just for a little abstraction here. Great idea, too costly. So let me just show you the punchline here. The way that this problem is solved is by having multi-level page tables. So we're taking our page table structure and turning it from a dense structure, a single table, into a sparse tree data structure. Everybody's favorite, I'm sure, after assignment 5, right? So each node has 512 entries. 4,096 divided by 8 is 512. And so basically we take the incoming virtual address, we take the virtual page number, we break it into chunks, and we use each chunk to do another level of mapping. So now we have a page table hierarchy. Okay? And so since most of the time our address space is going to be very empty, and we have large tracts of our virtual address space that are completely unused, that means that we can have at a certain level, we can have null for the entry. So the valid bit is 0, the rest of it is null, which means we don't have that entire subtree. Which means that you can end up with a page table structure for a process that's only a few tens of kilobytes, maybe a few hundreds of kilobytes, but definitely not 512 gigabytes. Okay? So turning this into a sparse data structure makes all kinds of sense because these address ranges typically are so empty. Okay? Let me just show you a little bit more. I already talked about this since I know we're over time, and I hate going over time. So Intel 64, let me just show you how this works. We have 48 bits of address. 12 bits are for virtual page offset, physical page offset. That leaves 36 bits for the virtual page number and physical page number. Okay, so I talked about this. There's a 4-level hierarchy. 36 bits divided by 4 gives you 9 bits at each level. Remember, 2 to the 9 is 512. 512 times 8 bytes per entry is 4 kilobytes. So just the math works out perfectly for that way of mapping the hierarchy. Let me see what this is doing. I have a picture here somewhere. I think it's on the next slide. Level 1, page global directory. That's the single node that is the root of everything. If you have an entry for a particular address range, then the next level is the page upper directory. Again, if you have entries below that, then it would be the page middle directory. And then the final level is the page table. Okay? So it looks something like this. This is the picture that I really wanted to get to. Page directory base register points to the root of the page table hierarchy. And then each level, again, the MMU will descend this. It'll look in the page global directory. If the entry is, the valid is 0, it doesn't even try, just false. If the valid bit is 0 and the rest of it is 0, then it knows there's not even anything to access. But if we have part of the address space, then you can go ahead and descend down the hierarchy and do the lookup. Now, let's see. It's 11:58. I don't want to keep you any longer. Are there any questions about this? There's a massive issue with this as well, but I'll tell you about that next time. So I will see you next time.